So this automation lunch and learn, we're going to cover how Metrology.net drivers are put together. Is going to be the main focus of this. So, and I'll do a little things that'll be like the NCSL, the way they want to do things, and the training organizations out there, where we want to come in there and we want to actually have some learning objectives so that people can have some walkaways with this. So the learning objectives, I think, in this one is going to be get an idea of how object-oriented programming works in the VB.NET and other .NET architectures. Talk a little bit about the threaded automation and how the actor paradigm runs. So the actor paradigm, we use it all the time. It's basically the core behind Windows and how Windows does everything. So give you guys an intro to what we're trying to do with Metrology taxonomy. And this is a bigger standard we're trying to create for the community, not just around Metrology.net, but the Metrology community in general. Do some basic things with some measurement uncertainties. We're not going to get into all the ins and outs of 17025 measurement uncertainties, but we want to show how that's put in there. And then one of the biggest features I saw of this was how to customize your uncertainties without having to go back in and make code changes. So that was one of the things that I think is important, because a lot of times our automation and our uncertainties are so tightly bound that we've got to go back and rewrite automation every time we need to change our uncertainties, and that becomes very costly over time. So a little bit about the company. Most of you guys already know me, so I won't get into this a whole lot. So we've been writing MetCal procedures for years, and we've got a large library of MetCal procedures. Around 2013 is when we broke the ground on developing Metrology.net, and we had our first customer up and running in 2015. So it's been around for about 4 years now, and we've been doing upgrades to it over the years. So we also have CalLab Magazine. So for some of you guys, you may know us from that regard. You're going to see in a lot of my slides, you see up here where you've got this little hammer chasing the nail. I like to put that in to a lot of my slides, because what happens a lot of times, if the only tool we have in our toolbox is a hammer, then every automation problem looks like a nail, and we beat it to death with our hammer. And that causes us a lot of problems in things.
I like that analogy.
So anytime I get into anything with automation and software in general, I've always found it good to start with a problem statement. So before you start talking about how you're going to solve the problem and all the things that are important to that problem, that you sit back and you get the problem defined. And you start from your problem definition before you even start thinking about implementation. And that kind of helps that hammer and nail scenario, is once you've got a good definition of the problem, then a screwdriver may do the work better than your hammer. So you don't always have to beat something into submission. So when we started this out, the problem that we saw as a company is we've got several companies around the world that are writing automation, or that we're writing automation for. And we needed a more powerful tool that we could go out and write our automated calibration in. We needed to put this together to where we could have a standardized measurement process independent of the standards that were used. We wanted to get that process definition down to where standards became interchangeable. And our first problem that we solved with Metrology.net, what allowed this to come together, is we were working with a company over in Turkey that was working with Turkey's National Metrology Lab to deliver a turnkey automated solution with all new standards to Saudi Arabia's National Metrology Lab. And our business problem was we didn't want to spend a year or 2 years in Saudi Arabia testing our software around the standards that were getting delivered for them. So we needed to build a solution that allowed us to test code in the US, allowed the Spark calibration we were working with in Turkey to test code, allowed their national metrology lab to test code. So when we finally got to Saudi Arabia and delivered the turnkey package, that we didn't have to spend months on end in Saudi Arabia testing that code. So we needed to get that metrology process that was interchangeable, knowing that our standards are going to be vastly different. So then, them being a national metrology lab, we need to be able to tie their metrology process to their uncertainty calculations. And we knew that their uncertainty calculations were going to be vastly different, but we didn't want to have to rewrite all the metrology processes as we were changing the uncertainties. So, and then the other thing we wanted to do was maximize the reuse of things without the code change. So we didn't want to have 5 different copies of the code. We wanted to have 1 copy of our UUT code that we could deliver to the guys out in Saudi Arabia. So in building all of this, I've started putting this pyramid into my slides because we start seeing that the automation that we're doing in the industry is very different as we go up and down the pyramid. So when we're at the top of the pyramid, we see that the national metrology labs and the primary labs out there, they're going to have a lot of measurement nuances, things that they need to keep track of. You know, what's their local gravity? You know, there's a whole bunch of little different things they need to keep track of because they're at the finest edge of the measurement uncertainties. As we move down the pyramid and we get into things that are a little bit more production oriented, we start seeing that their biggest problem at that bottom end of that pyramid is going to be flexible standards. And there we're going to see a lot of turnkey systems. There's not a lot of turnkey systems you see go from NMI to NMI to NMI. Most of those NMIs, they're going to come back in and they're going to start customizing those turnkey systems to what their needs are. So each NMI out there kind of has their own idea of how to do metrology and interchange things. So what we started working on, and this comes out of the NCSLI 141 Measurement Information Infrastructure and Automation Committee. And if you guys want to join in on that, we meet every Monday at 2 p.m. Mountain Standard Time. So, but what we were looking at inside of that group, and this is that overview of taxonomy, we were looking at the different elements out there that sits back in to where you've got the customers, and right here in the middle, you got the certificates of calibration, and there's, you know, billions to trillions of certificates of calibration. And as we want to start exchanging MII information, we want to start exchanging information in metrology, we started looking at how do we get that data back and forth. So right now in the industry, you send something out for calibration, you get it back. 99% of everybody is going to get back just a certificate of calibration that's either printed or in a PDF format. And we want to start making, in the MII group, we want to start making that data usable. We want to start making it to where when we send our calibrator off to get calibrated and we get it back, that we get calibration data back that we can put into our system so we don't have to go in there and manually enter all of that calibration data. And what we started noticing in the group was we needed something to make that data usable. So when I get back a whole bunch of data points, how do I know what that data point is and how that data point applies to my calibrator and how I can use that? And that's where we started looking at this taxonomy being the glue that builds all that or binds all that stuff together. So now what we were looking at is you've got the customers to where the customers could send in a piece of for calibration and they could give you all of their data points that they wanted you to calibrate. You could collect the data on those data points and give them back the results. And that's kind of what's at the heart of Metrology.net, is getting that to where we can start working with the data exchanges to where we're not dealing with PDF certificates. So this is just a quick overview of what we're trying to do with the metrology taxonomy. And taxonomy comes from when we start talking about the tree of life and all the different life forms that we have, from plants to animals to mammals. It's that categorization. And what we want to do with the metrology taxonomy is we want to take all of our measurements and categorize them and classify them so that when we get something, we can grab a tag that'll give us information about what that is. So this just kind of shows how we come out from a root, and we've got source and measure are the next biggest divisions. And then out of source and measure, we'll have, you know, amps and volts and resistance and all of those different things. Then as we break volts down a little bit more, we'll have AC sine wave for the volts, and we'll have DC volts that come out of a device. And you see over here with this implementation, where the implementation, how we're going to do that becomes the unknown. But we've got this standard that we're going to apply to, is we know what it is by a domain. Once we're in that domain, now we can start digging out things that become more and more specific to that domain. So the first thing that people have to wrap their head around with Metrology.net is going to be that we're test point driven. Okay, so the test points exist first, and then we automate those test points. So we grab those test points, and then we go in and we automate them. So that takes a little bit of time for people to wrap their head around how we automate the data points, as opposed to having a script that's generating the data points inside of the script. And then, as you can see, the core of all of our data points, we're going to have our nominal value, our upper and lower limits, our unit of measure, and inside of there, we're going to have that taxonomy that's going to say this is what that data point is. So now as we download that data point out of our test point server, now we can start getting very specific in the units or in the domain we want to work with. So this is an AC voltage domain, and we need to have the voltage and the frequency in order to understand how that works. So we pull the data point down, we got voltage and frequency, we can determine if we can do that data point or not. But we can also have extra data, like might be range, impedance, and other things. So as we were putting this together, we wanted to get away from being any single platform dependent. So any system that can come in and authenticate with the server, download the data points that it wants tested, iterate through those data points, and push the results back up to the server. Now we're talking about something that's Metrology.net compliant. In the bigger picture of this, we're talking about something that can stand the test of time, if that makes sense. Because over time, you know, we don't know what programming language will be the best language to use 20, 30 years from now. But I can pretty much rest assured my 3458 data points haven't changed in the last 20 or 30 years from when the 3458 was first put on the market. So that allows us to not think about something in terms of the language we're using. It allows us to start thinking about the data that we want to collect against an instrument and implement the language later. So now we're going to start getting in the heart of how we built the Metrology.net driver system. So back here, any language that you're looking at that you want to use, you can build everything yourself in LabVIEW and in HPV and Java. You can pick the language you want to use, download your data points, pick them up, use them. In Metrology.net, we wanted to kind of simplify this. So I have this 80-20 split that you're going to see in the two different parts of the green. And that 20% is the code that needs to be written that's specific to the device and the measurement process you want to do. That 80% of it is something that we use inside of the code that we can reshare. So when you look at each one of these blocks up here, you can see that this test base, test base, test base, test base resides across all four of them. Well, what happens in that test base is we didn't rewrite that code for each one of those. We actually shared that same code. And that's one of the powers of object-oriented programming, is you don't have to rewrite everything. You get to have a piece of code that you can inherit. And when you inherit that piece of code, it allows you to share that piece of code so you don't have to write it again and again and again and copy it and copy it and copy it. So, and then this blue part here, this interface, this is kind of how the drivers work together. So this custom code that you're going to write inside of your specific test process, it's going to talk to the interface of a measurement device, and it's going to talk to the interface of the source device. And it's never going to know specifically what's behind that interface. And that's another thing of object-oriented programming is you get to talk to things with interfaces, with classifications of what they do. So instead of thinking about it as a 5500 or a 5700 and the commands you have to use, you think of it as a source volts AC or a source volts DC interface, and you get a lot of flexibility in how you're able to work with that device and a lot of categorizations that work. So, and then this red lines down here I have is the I/O between them. So what we've done inside of Metrology.net is we've threaded the system with the I/O with the actor paradigm, which allows us to reach out to the device and use the device similar to how you would press a button on like a Windows form. So that's how the actor paradigm runs, is when we want a source volts DC out of our calibrator, we're just going to tell it source volts DC, and it's going to generate that voltage DC, and then it's going to turn itself off on how we want it to run. But we never have direct binding to each one of these objects. So each one of these blocks out here exist as their own tools, so we can share the resources back and forth. And what that allowed us to do was to run multiple calibrations on a single computer at the same time with a single GPIB card, because the GPIB I/O stands up as its own interface, and we don't have to bind into it and lock that resource down. We get to share that resource. So now, before I dive into the code, I'm going to give you guys a real quick overview of how this runs. So every one of our processes, our test processes that sit in Metrology.net, they're going to bind up to this test process, this blue interface, but you can see we've got a 5720 specific version of this. And every one of these run processes, or every one of these test processes, is going to have a run function. And that's the function that we're going to call. So now it doesn't matter if we're doing something that's a temperature calibration, a voltage calibration, an RF and microwave calibration. We're going to call a run function, and we're going to give that run function a set of test points. And then you can see inside of the pseudocode here that we're going to reset our standard, reset our 5720. Then we're going to call our reset function on our device under test. Then for each one of our test points, we're going to set up the unit under test, set up our standard, enable our standard, call our measurement process. Then we're going to save our results off to the database, disable the standard, and we're going to go into the next data point. So we write everything in Metrology.net from the, I get a set of data points, I'm going to run those data points or process those data points and push the results back into the server. So however you want to write your code below this test process interface, you get to write that code any way you want to. So I'm going to jump into the code review, and what I want to go through is going to be a 5720 AC voltage driver. Then I want to look at how the source volts AC subdriver works, how it calculates the measurement uncertainty, how it calls off the 5720 driver, okay, and then come back in and look at some of the UI options, come back in and look at how we can change that process to a 5720 that's characterized. So now we can calibrate long scale voltmeters because we characterize that 5720. Look at how those uncertainty calculations run and how we can create a characterization object. Then how we could interchange that with a 5520 or a transmil. Then we'll come back in and look at how the filters work in this a little bit. So jump right into the VM here. So this right here, How many of you out there have programmed in something like Visual Basic or an object-oriented programming language?
I was going to say I've done a lot of programming, but it's fairly dated. And so the more modern techniques, once you get beyond Classic Basic and Rocky Mountain Basic and other similar, even earlier languages, I'm a little no experience on.
So there's a lot of power that happens. So this up here where we're inheriting from test process. So this class out here, so source volts AC, gets everything that's inside of that test process class. So you'll see over here when I come into a sample programming and I put this inherits in and I hit the enter, it goes and it stems out my code. So it puts in all of my requirements of things I need to write. And right here, you see it puts in my run function that I've got to come in and write that run function. So it'll help me as a developer in what I need to do to come out and stem this code out. So then in every one of these, we're going to have this creation. So we've got to have a new function that sits in there. We have to have information about what it is. So this is just header information. What is my unique test ID? What is my test type? So this says how I'm interchangeable. What is my name, 5700? What is my description? This is what version am I? What unit of measure am I? Who created me? So that sits up in the header information, and it's a requirement inside of Metrology.net. Then we can start putting in our parameters. So this is telling the system that you have to tell me the frequency and voltage. If you don't give me the frequency and voltage, I can't run. And then there are no additional parameters that it wants to know about inside of here. This piece of code here with the equipment, I'll reach down into here. We're going to say that it wants to see a source volts AC. And it wants to have a 5700 source volts AC driver. So inside of this reference, it's saying I need a resource, and it's got to be a 5700 series AC voltage source. And then here it's saying for my UUT driver, you've got to give me an I measure test point controller. So this is just saying I need these other resources. Can you please add these resources in so that I can use them? And I'll jump back real quick in a slide to reference this out. Oh, come on, you computer. Fighting with my computer today. So here you can see that our test process, it's going to need a measurement device, and it's going to need a source device for it to run a test process. So that's how it reaches out to those references. So now this 5700 is going to be implemented by this device driver, which is going to be our source volts AC 5700 as its full name that sits in there. Again, we've got our creation, our header information. Here we've got the equipment required. This guy's going to want to have a 5700 driver. Now, I build my drivers in this 3-level stack, so I get reusability of the drivers. So, and I also get the ability to lock them down so I can run fully threaded calibrations without using the resources at the same time. So an example of the advantage you get out of this layering is that you can have a workstation that's got a 3458 and a 5700 on it. Say you characterize your 30 or your 5700 with your 3458 every day, right? So now you can use the 3458 to characterize your 5700, go out and run calibrations with your 5700. But at the same time, you could use that 3458 to go out and calibrate other devices under test, as long as you weren't using that 3458 to characterize your 5700. So you get to reuse that. So that's what we get out of this 3 levels, is we get a lockdown specific instruments and specific functionality of instruments.
Using the 3458 or whatever instrument to do task A and task B, are you saying that they could simultaneously be doing two different tasks? The measuring device go measure something in a certain calibration task, and the 5700 or the source doing a calibrating of a meter. Are you talking about that type of simultaneous metrology?
Yeah. So you could have the 5700 in the morning characterize itself with the 3458. When that process is done, you can use your 5700 to go calibrate meters, and you could use your 3458 to go out and calibrate function generators or something else. So that's what you would get in simultaneous. So as long as the test process isn't using the resource, that resource is free to be used in other test processes.
And that same computer is running that as a controller of the various instruments on the system. So the computer is time sharing its tasks simultaneously.
Yep, exactly. You get time sharing out of the devices on that workstation.
Okay, thank you.
So, but inside of here, when we're talking about our source drivers, or when we're talking about our AC source, we're going to talk to this guy a little bit different. So we're going to have functions that we're going to call, which is a reset function. Then we're going to have a setup function, which is going to set it up to source volts AC. And then we're going to have a function that's going to be output on, so disable and enable. So that's how we're going to talk to this device. So we're not talking to it in terms of its commands that are going out. We're talking to it in terms of the functionality that we want out of this. And the functionality gets wrapped up into the simple interface of set yourself up, turn your output on, turn your output off. And that allows us to take something like a 5500 with our measurement process and make that interchangeable with something like a signal generator, talking to it in this simpleized interface. Then you'll see here that this is going to be talking to the device. And down here, we're going to set a property on our calibrator. Our mode is AC voltage. Our frequency is set to a value. Our voltage is set to a value. And then when we enable this, the driver comes in and looks at all of its settings and says, I'm going to go in and look at, you want to turn me on? Mode is AC voltage. Here's how I send that command. Here's how I turn my output on. So it allows us to wrap up a lot of functionality into a very simple interface to where we can get a lot of interchangeability across how we're running things. And in some later training, what we'll do is get people into where they have this level of training. We offer it to any Metrology.net users. We offer them 2 seats in a advanced training course here in Colorado at our facilities, where we'll bring in the equipment and let you sit down and run some calibrations and teach you how to write all of these drivers and give you source code for this. So now I'm going to jump back to my AC voltage and the measurement process, now that we've got an idea of the equipment. And we can see in here, based on our pseudocode, that we're coming in, we're setting up our unit under test. We're going to run our test setup. This just allows us to set up some things for the device. As far as what we're going to run, it allows us to set the number of measurements we want to take, and it'll let us set what the UUT address is what that piece of code will do. Then we're going to set up our source. So you see we're talking to the 5720 or 5700 with just source volts AC, go reset yourself. And then here, same thing with the unit under test, just go reset yourself. Now for each one of our data points, we have this loop. And you see how we have this filter here? So I'm going to right click on this filter, and I'm going to go to the definition. And here we have a filter of volts. We're only going to accept volts that are between a millivolt and 1100 volts AC. Anything else, we're going to skip that data point because we can't do it. And then here we're going to skip anything that's less than 9.5 hertz and anything that's bigger than 1 megahertz. So the idea behind Metrology.net on the drivers was to build them like we do HTML. And as we're building out our HTML interfaces, anything the HTML, the browser doesn't know how to do, it just skips it. So here, if you give this a whole bunch of DC voltage data points, this AC voltage system is just going to skip it because it's DC voltage. It doesn't know how to do DC voltage. So then back up here, we're going to check our connections. And we allow people to do text-based connections, picture-based connections, and the users can see that inside of their browser. And anybody who's has their browser to that calibration can see the connection message, and then it'll go away once one person is connected. Then here you can see we're sending it the data point or the test point that we want to do, and we're telling the calibrator to set itself up. If the calibrator can't set itself up, we fail there, give the user a message, and we skip that data point. Then we reach out and tell the driver to enable itself. And if we're not able to enable itself, we might get a reason as to why, to give the operator some information like a boost amplifier is required and you don't have it. Then if that passes, create a test result. And then this little wrapper in code here with this for each, this is going to run the measurement the number of times that we want to measure it. So if the user wants to collect one data point, we'll execute the loop once. If the user wants to collect 15 or 20 data points, we'll iterate through it that amount of time and collect those values. And then each time here, you see we're adding the measurement to our measurement results object. So that object is able to hold a single measurement result or a collection of measurement results, grabbing the average and the standard deviation out of that for our uncertainty budget.
Does that happen at the operator at time of use or with the procedure writer as he's defining the process?
Well, the procedure writer, as he's defining the process, he's going to give you the option to set that it's doing multiple measurements or not. And then the user at runtime gets to choose how many measurements he wants to take.
Okay, thank you.
So, and then you can see here that we're saving the results. So this saves it each iteration. So now if that calibration stops, he still has his value. And then here you see we ask the source volts AC. We want the measure and, so we want its set value, and we want the uncertainty of that set value. So not in the AC voltage, but in the resistance side of things, the calibrator has a fixed value for its resistance. That allows us to reach back and ask the calibrator, hey, I wanted 1.9 ohms, but you were really what resistance? So that would allow us to get back the value as opposed to the uncertainty. So this is going to make a call to the driver, and inside of the driver to get the uncertainties, you're going to see that we're first going to look at the model. Is it a 5700 EP, a 5700, 5720, or 5730? So we can go to the 5720 uncertainties. And here we've got the 1 year, 95% uncertainties out of the manual coded in. So here it's just going to look at the voltage we're looking at, look at the frequency we're looking at, and it's going to pull the value right out. So you can see 80 parts per million times the voltage plus 4 microvolts is what it's adding. And now you can see inside of here, we're going to pass those uncertainties, but we're putting them in the test result. So the test result is also going to have from the UUT the repeatability of the number of measurements and the resolution that was set in the data point, so we can write that data back into our uncertainties. So the only thing missing here for a 17025 calibration would be what is the traceability uncertainty of my calibrator. And that would be something that we'd either have to code in or override. And after I go through the drivers, I'll reach back in and show you how we have this set up to override.
So as you have it set up for use with different calibrators. Okay. Now you showed that, you know, this intended use is probably with a 5700 class calibrator. Now, theoretically, you could have for something, you know, a 5500 class, a fluke or a transmill or a whoever, in this list of possible equipment. Now, there could be some chances that the specs of that instrument don't make it. You know, it's not accurate enough of the calibrating standard to do the calibration task of the
Yes.
unit being calibrated. Where is that flagged or found?
Get in
And
here
is it
real quick and I can show you.
okay?
So what will happen is if you're running the calibration, and we'll look at the AC voltage here 1 year. So you're sitting here looking at this and you're saying, hey, this 3.1 TUR isn't good enough for me. What you can do in Metrology.net is you can say, I'm going to clear that result so it's not tested. Then you come over here and say, run my untested data, update my work order. And then you can say, run those tests on my 5790.
Okay.
Because it's on that island of our data points, we can choose where we want to do those data points. The next update is going to give us the ability to come in here and say, check, 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 run our check data points on this other system. So we can go in and control where those data points get run.
Okay.
So, and then you can see out here, we're also calculating the risk and confidence. So sometimes, and I have a really good example up here with a different work order, that right here. So this Additel device, if you look at this, you're 1.3 to 1. So that looks really bad, but look at your confidences. You know, your confidence is if you're trying to hit a 70%, all but this one data point hits that confidence point. So it's doing your confidence analysis while it's running the calibration.
Okay.
Is at the process level, not at the instrumentation level.
Okay.
So inside of this right here, this test type, test process, source volts AC, this is that interchangeable level where anybody that's got a test process, source volts AC is interchangeable. So if we look over to our characterized calibrator, which is going to give us more accuracy, inside of here, you can see it still hits the same test process type, but when we go down to the equipment required, we want a source volts AC for our calibrator. We still want to have a 5700 driver in here. But here we're saying anything that can measure volts AC, we can use that to come in and characterize me. We try to empower the technician rather than limiting what he can do with his calibrations.
Okay.
So now this process is going to have 2 for loops. The first loop that sits in here is going to be running the characterization. So here, for each one of our data points, we're going to run a characterization. And if I scroll down here for each one of our data points, we're going to actually calibrate the device. So this first looks at our characterization and says, is characterization required equals false? So here we go through and look at all of our characterization data points, and we look at the dates on them and see if we're old. If we're old, then we're going to say, hey, characterization is required. Or if we don't have a frequency and voltage for that characterization data, then we can say we can characterize it. So instead of in the morning with our 3458 or our 5790, having to characterize all the data points that we need on our 5700, we can actually configure the process to go in and just characterize the data points we need. And throughout the day, as we need it and then use it for the next 24 hours. And that's just how I wrote this particular algorithm. So anybody can come in and write the algorithm the way they want to. So now when we look at the characterization object, this is one of the powers of object-oriented programming, is we have this piece of data that stays with that 5700 driver. Why that 5700 driver is in memory? Object-oriented programming lets us put function and data together. So as long as that driver is instantiated, it has its characterization data with it. So it's going to keep it. And now we can get data points. We can check if it has a data point. We can check we can add data points. This is going to look if it has the data point. It will override it or add it. So it's an add or override. So now our characterization routine can come in, make the measurements, and save our characterized data. So now that when we're running our measurement process, you see we still got the setup, we still got the output enabled if it's good, but now we're going to go out there and we're going to grab our characterized data. Okay, and we're going to use our characterized data. We're going to grab that value and add that away as our measurement. Okay, so now we're storing away our nominalized value of the measurement. So we can offset what corrected value. And then here, when we want our uncertainty, we're not calling our source driver anymore. We're calling our calculate uncertainty. And if we look at this definition, now we can see we're using our 5700 24-hour specs and our DMM's uncertainty for making that measurement. So now we're grabbing the 5790 specs, RSSing it with the 5700's 24-hour specs, and posting that back as our value. So our UUT code never changed, but now we can calibrate our UUT with a characterized 5720, or we can calibrate it with a regular 5720. And if we wanted to, we could reach over to something, this right here is a 5500. So if you look at this driver, we've also got a 5500 driver that we can calibrate things with source volts AC. And if you look down here, we got a transmil driver that'll do the same thing. So that's where we get our interchangeability of our devices, is we interchange them at this run process, where we download the data points and we iterate through the data points. So Jack, back to your question. Somebody could write a driver that would say, I'm going to look at my measurement uncertainty, and if I'm not 4-to-1, I'm going to skip that data point, or I'm going to ask the operator, does he want to do that? That's something that could be coded into the measurement processes. It's just that's not how we're coding our measurement processes.
Okay, thank you.
So now I'm going to jump back to the uncertainty override. So our measurement processes collected all of this data. So we got our voltage, our frequency, our range, our impedance. We added back to it our calibrator that was used, the interval of our calibrator, our resolution, our repeatability. And now we can pass that to an overridden uncertainty calculator. So to show you that in the user interface, I have a 34450 set up. On DC voltage here, if I'm going to run DC voltage, you see if I'm using a 5500, I have no overridden uncertainty calculators. But if I set it to a 5700, now I've got 3 uncertainty calculators that I can call right after I post my measurement. It's going to call the uncertainty calculator to put the uncertainty in that's an override to my uncertainty. So now that's what this is going to do. After I do my measurement, I post that up. I'm going to take those values and send them into my uncertainty calculator, which is going to run that calculation. And we do that here with a spreadsheet where we put in our inputs. We wire up through some fancy, Excelology. to where our uncertainties are going to be calculated in something our accreditation body is used to seeing. And then we're seeing here 7.09 e to the minus fourth. And here we're seeing 7.8 E99. But it allows us to come in and take our uncertainty budgets that we're handing off to our accreditation body in our metrology software to where our scope of accreditation uncertainties are not different than what our software is running. Does that make sense?
Yep.
So anybody who comes in and runs metrology.net, they're going to get copied to some code that's up on the SASO or up on a GitHub server under CalLab Solutions SASO. And that code is shared amongst everybody. So you will have the ability to reach in and grab that code and use it as samples for building your own drivers. So learning objectives, I think we hit all of them, though we didn't get into all the features of object-oriented programming. We did talk about threading, automation, and the actor paradigm, a little bit of metrology taxonomy, some basics of the 17025, and then how you can change your code, or you can tie your code to uncertainty calculations that allow you to vary them. And I'm going to jump back to this slide for just a second. If you look at Quality Magazine, October 2015, volume 54, number 10, that issue of Quality Magazine actually has an example of how you can send a set of name value pairs off to our uncertainty calculator and use metrology.net to do nothing but calculate measurement uncertainties for you. So any questions?
I can provide the REST documentation with that information to anybody if they want it, Mike.
Okay.
I can't see any other questions from my side.